Have you ever wondered about the true nature of reality and the universe? Ah, the enigma of reality. It's a question that has puzzled humanity since the dawn of consciousness. But what if I tell you that the answer to this age-old question might lie in the realm of the tiniest particles in the universe? Welcome to the fascinating world of quantum physics. Quantum physics, or quantum mechanics, is a branch of physics that dives into the realm of the minuscule, the atomic and subatomic levels. It's a world where particles can be in two places at once, where they can spin in two directions simultaneously, and where observing a particle can actually change its state. Strange, isn't it? But that's the quantum world for you. A place where the impossible becomes possible. This revolutionary field of study has completely transformed our understanding of reality. It's not just about studying small particles, but also about understanding the fundamental nature of the universe itself. It's about probing into the heart of matter and energy, diving into the very fabric of the cosmos. But why is quantum physics so important? Well, it's because it's the only theory we have that can accurately describe the behavior of the universe at its most fundamental level. It's the theory that underlies all of modern physics and has given rise to technologies that have changed our lives, from computers and lasers to nuclear energy. However, quantum physics is more than just a scientific theory. It's a philosophical enigma. It challenges our understanding of reality, forcing us to rethink our notions of space, time, and causality. It's a field that blurs the line between science and philosophy, between the physical and the metaphysical. So, how did we arrive at this intriguing field of study? What were the key discoveries and breakthroughs that led to the development of quantum physics? And how has it revolutionized our understanding of reality and the universe? So, how did we arrive at this intriguing field of study? Let's dive into the history of quantum physics. The story of quantum physics begins in the late 19th and early 20th centuries. At this time, the world of physics was dominated by classical mechanics, a theory rooted in Isaac Newton's laws of motion and gravity. But as scientists delved deeper into the mysteries of the universe, they began to uncover phenomena that classical mechanics couldn't explain. Enter Albert Einstein, who in 1905 took a deep dive into the nature of light. His work on the photoelectric effect suggested that light wasn't just a wave, as classical theory posited, but could also be described as particles or quanta of energy. This was a groundbreaking revelation, a dramatic shift from the wave-like view of light that had been accepted for centuries. Not long after, another revolutionary idea surfaced, this time from physicist Max Planck. In 1900, he proposed that energy isn't a continuous, flowing entity as previously thought, but rather comes in discrete quantized packets. This concept was nothing short of radical, completely contradicting the classical view that energy could assume any value. These groundbreaking ideas from Einstein and Planck began to challenge the long-standing principles of classical mechanics. They laid the groundwork for a new theory of physics, one that would delve into the smallest scales of energy levels of atoms and subatomic particles. This was the birth of quantum physics, a theory that would redefine our understanding of the universe. It set the stage for a new model of the atom proposed by Niels Bohr in 1913, which explained the spectral lines of hydrogen and the subsequent mathematical formalism of quantum mechanics developed independently by Werner Heisenberg and Erwin Schrödinger in 1925. From the particle-like nature of light to the quantization of energy, these early developments in quantum physics challenged the status quo and set the stage for a new understanding of the physical world. These early developments set the stage for a new model of the atom and the mathematical formalism of quantum mechanics. A new era in physics had begun, and the world would never be the same. In 1913, Niels Bohr proposed a new model of the atom based on quantum theory. The model was revolutionary. It suggested that electrons orbit the nucleus in distinct levels, or shells, and light is emitted when an electron jumps from a higher energy level to a lower one. This model was a quantum leap, pun intended, from classical mechanics, and it successfully explained the spectral lines of hydrogen. But the quantum world was still a mystery, and the stage was set for two brilliant physicists to further unravel it. Enter Werner Heisenberg and Erwin Schrödinger. These two gentlemen independently developed the mathematical formalism of quantum mechanics in 1925, each one providing a unique perspective on the nature of reality. Heisenberg's approach was known as matrix mechanics. It focused on observable quantities like position and momentum, and it was based on the radical idea that these quantities don't have definite values until they are measured. This was a sharp departure from classical mechanics where quantities like position and momentum are always well defined. On the other hand, Schrödinger's approach, known as wave mechanics, was based on the idea that particles have wave-like properties. He proposed that particles like electrons are described not by definite paths, but by wave functions that give the probabilities of finding the particle in different places. This idea of wave-particle duality was revolutionary, and it further blurred the line between the macroscopic world we see and the microscopic quantum world. These developments led to one of the most important principles of quantum mechanics, the uncertainty principle. This principle, formulated by Heisenberg in 1927, states that it is impossible to simultaneously know the exact position and momentum of a particle. This isn't due to any limitations in our measuring instruments, rather, it's a fundamental feature of the universe. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not just a strange quirk of quantum mechanics, it's a cornerstone of our understanding of the quantum world, and it's something we'll explore in greater depth in our next scene. In 1927, Heisenberg formulated a principle that would shake the very foundations of our understanding of reality. This principle, known as the uncertainty principle, states that it is impossible to simultaneously measure the exact position and momentum of a particle with arbitrary precision. Now, why is this significant? Well, consider for a moment that you're trying to track a tiny particle like an electron moving in space. According to classical physics, you could measure both its position and its momentum, that's its mass times velocity, precisely, to as many decimal places as you like. But quantum physics throws this idea out the window. Heisenberg's uncertainty principle tells us that the more precisely we determine a particle's position, the less precisely we can know its momentum, and vice versa. It's like trying to catch a slippery eel. The harder you grip, the more it slips away. But it's more than just a pesky limitation on our measurement capabilities. It's a fundamental aspect of the universe, a built-in fuzziness that's part of the very fabric of reality. It tells us that at the smallest scales, reality is not solid and predictable, but rather cloudy and ambiguous. This principle was a radical departure from classical physics, which held that the universe operates like a well-oiled machine, with every particle moving predictably according to the laws of motion. It shattered the deterministic view of the universe, replacing it with a probabilistic one, where outcomes are not certain but rather described by a range of probabilities. And if that's not mind-boggling enough, the uncertainty principle also implies that particles can pop in and out of existence in empty space, a phenomenon known as quantum fluctuations. These fluctuations are the basis for the theory of quantum field theory, which describes the fundamental forces of nature. So, you see, Heisenberg's uncertainty principle is not just a quirky aspect of quantum physics, but a fundamental principle that shapes our understanding of the universe. This principle, along with the other developments in quantum mechanics, has had profound implications for our understanding of reality and our place in the universe. Quantum mechanics has not only changed our understanding of the universe, but it has also transformed our society in profound ways. Its unique understanding of the microscopic world has led to the development of numerous technologies that we use daily. Transistors, for instance, are the building blocks of modern electronics. From the smartphone in your pocket to the computer on your desk, transistors are at the heart of these devices. Without the quantum mechanical understanding of how electrons move in a semiconductor, the development of transistors would have been impossible. Next, we have lasers, which are another wonderful offspring of quantum mechanics. The principle of stimulated emission, a phenomenon where an incoming photon provokes the emission of a second identical photon, is a direct consequence of quantum mechanics. Today, lasers are everywhere, from supermarket barcode scanners and DVD players to cutting-edge medical equipment and industrial machinery. Then, there's nuclear power. Quantum mechanics provides the basis for understanding nuclear reactions. It helps us comprehend how atoms can split or combine, releasing enormous amounts of energy in the process. This understanding has not only led to the development of nuclear power plants, but also the field of nuclear medicine, which provides new ways to diagnose and treat diseases. Beyond these practical applications, quantum mechanics also has profound philosophical implications. It challenges our understanding of reality, suggesting that at its fundamental level, the universe does not work in the deterministic, predictable way we might expect from our everyday experiences. Instead, it's a world of probabilities and uncertainties, where particles can be in multiple places at the same time, and reality only takes shape when observed. While quantum mechanics continues to pose more questions than it answers, it remains one of the most successful theories in physics, forever changing the way we perceive reality and the universe.